Welcome to the video. The context of the video is finding optimized airline route using weighted graphs. The context is delivered by team members Sivapriyan B, Yajnesh M, Arul Kumar A, Darun SP, Santosh U, Punit Moti BS. Introduction to airline route optimization. Airline route optimization is crucial for making our travel efficient and profitable. It involves making strategic decisions about flight paths to enhance operational efficiency and customer satisfaction. So, finding an optimized airline route would make companies profitable and also to make our travel easier and convenient. The factors are influencing the routes are cost, distance and time, scheduling, and fuel consumption. The company's major goal is to reduce the fuel consumption, and the maybe like travelers' goal is to travel travel minimum distance or travel to a new area within a short duration of time or to spend minimum money on the travel. The cases may be any of the four, and we need to decide which should be prioritized and find the preferable path for that. To carry on, we need to visualize airline networks as a graph. Here, we consider the airports as nodes and the routes as edges. The airports may be Los Angeles, Tokyo Airport, or New York Airport. We may also consider Chennai, Coimbatore, Mumbai, Calcutta, Allahabad airports as the vertexes and the flight connections between them as edges.
See about the topic directed versus undirected graphs. Understanding the nature of connections between nodes is crucial for accurate graph modeling. Undirected graph. In an undirected graph, an edge between two nodes means travel is possible in both directions. For example, if there is a flight from airport A to airport B, there is implicitly a flight from B to A. This is generally not possible in case of airlines. Symmetric relationship, not inheritance directions. Unweighted graph. An unweighted graph is a graph in which all edges are considered equal, meaning no numerical weights, cost, distance, or time are attached to the edges. Directed graphs. Airline routes are best modeled as directed graphs. A flight from airport A to airport B does not automatically imply a return flight from B to A, or that the return flight has the same characteristics. Factors like wind directions, air traffic control regulations, and even time zones can make two distance directions. Asymmetric relationships, edges have specific directions. Weighted graphs. A weighted graph is a graph in which every edge has numerical value called a weight. Thus, this weight usually represents qualities such as distance, cost, time, capacity, fuel consumption, any measurable value for that connections.
Before we even optimizing the air route lines, we need a mathematical way to represent the entire air network. This is where the concept of weighted graph become essential. Here, the airports are considered as nodes and the possible flight paths between airports are edges. But the real power comes from the weights on these edges. These weights allows us to convert the real world complexities into a number that algorithms can understand. Here, the freight routes never be equal. One route might be shorter, another one be longer. The types of weights that are used in the air route optimizations or distance represents how long the flight path is geographically useful for estimating the approximate fuel and time. Cost includes the fuel cost, airport fees, crew cost, and the operational expenses. Fuel usage. Some routes consume more fuel due to latitude changes and wind. Next, travel time. Total time during the possible delays or holding patterns important for scheduling and improving the customer satisfactions. So, weighted graphs allows us to stimulate different routes, compare the alternatives, balancing efficiency, cost, and the safety, make data driven routing decisions. The structure become the foundation for applying the algorithms like Dijkstra, Bellman Ford algorithms. Once we represent the air network as a weighted graph, the next step is to clearly define what we want to optimize. This is what we want to objective and understand the constraints. Time. The aim is to get passengers to their destination as fast as possible, reducing the flight time, increases the aircraft ability, and improves the schedules. Cost. Airlines operates with a profit margins. Optimizing cost helps reduce expenses like fuel, landing fees, and staff hours. Fuel is the largest operational cost. Efficient flight paths helps the airlines to cut millions of dollars annually. Like real world constraints, air traffic controls restrictions. Aircraft must follow restrict air control corridors. Some regions may be restricted. Next, the weather conditions. Safety is always the first priority, so jet streams and winds can be change the flight path. Crew duty limits. Pilots and cabin crew have maximum working hours. A long route may require crew rotations. Maintain schedules. Airlines need to plan routes around the required checks and repairs. Here we can, from this, we can conclude that these constraints make the airlines optimization a complex real world problem. What looks simpler in textbook but becomes a challenging task that requires advanced algorithms, real time data, and smart decision making.
So now we are going to see about Dijkstra's algorithm. This is an important algorithm where we will be using these algorithms to solve the minimum distance or minimum cost required by the airports or airlines to compute the minimum amount of distance, so they can use these algorithms to get that minimum amount. So first of all, we will be talking about Dijkstra's algorithm. Dijkstra's algorithm is a shortest path algorithm which is used mainly on weighted graphs with non-negative weights. So if you are given a weighted graph with nodes, if you want to get the minimum distance or minimum amount of cost for traveling from one node to the another node, Dijkstra's algorithm is a very important algorithm used for that purpose. So in this algorithm, what we'll be doing is, so here is an example given uh, where there are set of nodes A to B, the weight is 10, A to C 20, B to D 15, C to D 30. So uh, there are set of nodes with weights given which represents an graph. For this, we'll be finding the minimum distance using Dijkstra's algorithm. So for this method, we will be using first we will be starting with the initial node where will be which we can take as A. So from A we will be from the point node A, we will be exploring all the nearby nodes where with the minimum distance or whatever the node adjacent to the initial node, we'll be marking the distance. Example for A to B, it is 10. So we'll be marking with the B node with 10, which is the weight of the node H. Next, the adjacent node of A, which is C, which will be marking with 20. Likewise, we will be marking all the adjacent nodes with their corresponding weights from the starting node. Uh, After marking all these weights, we'll be computing the minimum distant edge or minimum weight with the when seen with the all adjacent nodes. So here it would be A to B, which is 10. So we'll be now moving to the minimum distance node, which is B. From that B, we'll be repeating the same process while we seeing the adjacent nodes uh, to B, and we will be marking those the weights for the adjacent nodes of B. And with the uh, marked edges or weights, we will be determining which node to be explored further. So likewise, we will be computing the minimum shortest Here, for the given example, the shortest is A to B to D. If we are going to find the normal, or maybe if you are just directly linking the node, you will be getting a weight of 50, which is A to C to D. If you are using Dijkstra, you will be getting the optimal from A to D, which is A to B to D, and the total minimum cost is 25. So this is all about Dijkstra's algorithm. Next, we'll be seeing about another algorithm, which is Bellman-Ford algorithm. The Bellman-Ford algorithm computes the shortest path from a single source to all other nodes in a weighted graph that may have negative edge weights. So, what the difference between the Dijkstra's and Bellman-Ford algorithm is the involvement of negative edge weights, where in Dijkstra algorithm, you won't be having the negative edge, which is and plus in Bellman's according to this property, where you will be having negative edge weights. So, in case of, for example, here already it is given and graph with three vertices and weights represented where A to B it is 50, B to C it is a negative edge minus 10, and A to C it is 60. So what does this negative edge represent is it is not actually you can instead of distance you can actually say it as cost. So if it was usually it would be B to C was 30 and the cost of spending from B to C is 30 and the airline maybe the airline is giving a discount of 20, so the minimum cost required to travel from B to C would be 30, but since the airline is offering a discount, it is reduced to minus 20. So the total cost until the amount offered is you will be subtracting and you will be getting minus 10. So it is an negative edge. For this, you can't find the minimum distance with the help of Dijkstra. So you'll be going with the Bellman-Ford algorithm, where you'll be using the algorithm to find the minimum distance. If you want to get the minimum distance from A to C, you would be going in the straight path, which would be A to B to C, which will amount to 40. But if you are going through Bellman-Ford algorithm, it will be to 40, which is A to B to C, I mean to say. So, in using that weighted graph, weighted edge, you would be getting more further concession on the distance. So, it is all about Bellman-Ford algorithm. Next is another algorithm used for finding or computing shortest distance, which is Floyd-Warshall algorithm. Uh, Floyd-Warshall is an all-pass shortest algorithm, which means we'll be exploring all the nodes from the starting node. Here, an example is given. There are three airports A, B, C with corresponding weights. So if you want to get the, if you want to get the distance between A to C, you would be exploring from A to C with all the possible nodes, which is known as all pass shortest path algorithm. So the shortest distance between every pair of nodes in a weighted graph will be computed by traversing every intermediate nodes. So this is an efficient algorithm where you will be getting all the possible intermediate distances, and with the list of all distances you will be computing the minimum distance. So this is all about the algorithms used for computing minimum distances in airline or any other minimum spanning detections for a given set of graphs. Next, we will be talking about shortest path algorithm, specifically for Dijkstra's algorithm.
Now we are going to discuss about how Dijkstra's algorithm works. Let me see step by step process of Dijkstra's algorithm. Dijkstra's algorithm helps find the cheapest or fastest route between airport. Think of it like a GPS for airlines. It checks all possible paths and picks the best one. Let me start the first step of Dijkstra's algorithm. Mark your starting airport and set its cost to 0. All other airports start with infinite cost. Step 2. Pick the cheapest. Always choose the airport with the lower cost that you haven't visited yet. Check neighbors. Look at neighbor airports and see if going through your current airport make the trip cheaper. Mark as done as fourth step. Once you have checked all neighbors, mark this airport as visited. Step 5. Find the best path. Keep going until you reach your destination. The algorithm guarantees you found the cheapest route. Then we see a worked example, finding the optimal route. Let's apply Dijkstra algorithm to a simplified airline network. Our goal is to find the cheapest route from airport A to airport D. Consider the following simplified network with cost as bracketed weights on each route. A to B as $100, A to C as $150, B to D as $200, C to E as $50, E to D as $75. By applying Dijkstra algorithm, we compare possible paths and their cumulative cost. Path 1 A to B, B to D is A to B as $100 plus B to D as $200, then equal to the total cost of A to D as $300. Path 2 A to C, E to D, the cost is equal to the A to C $150 plus C to D as $50 plus E to D as $75. The total cost is $275. The optimal path based on minimizing cost A to C, E to D with the total cost of $275. Then we see a graphical representation of that worked example. Network graph. To better understanding the Dijkstra algorithm in action, let's visualize the simplified airline network used in our worked example. This graph represents airports as nodes and flight routes as directed edges, each carrying a cost weight. Then path 1 as A to B, D as $300, A to C, C to E, E to D as $275. The optimal path based on minimizing cost is A to C, E to D with a total cost of $275. This is the graphical representation of our worked example as named as a network graph. The visual representation clearly shows the connections and their costs, make it easier to trace the paths and apply optimization algorithm like Dijkstra to find the most efficient route.
I am B.S. Punitmati. I am going to explain about real-world airline application and benefits. These are the principles of weighted graph optimization extend far beyond theoretical experience, deeply impacting various aspects of airline operations. Here are some of the applications. These are scheduling, route planning, weather routing, and fuel optimization. First, we are going to see about scheduling. Scheduling is about optimization, flight times, and connecting maximum aircraft utilization and passenger consumption. Route planning determines the most coefficient and efficient path between the cities. It is about the cities short route for the cities. Weather routing dynamically adjusting flight path and route time to avoid weather conditions. Fuel optimization calculate flight path that minimize fuel consumption and major operation. Fuel optimization is used to reduce the fuel rate and the fuel used in the flight. These are some of the applications collectively lead to significant benefits of both airline and and their passengers. Reduce fuel cost, directly implicit profitability, improves punctuality. It is used to reach the passenger at the time to the reachable city. Efficient resource allocation, better utilization and aircraft crew and get space. It is used to better utilization is for passengers.